All right, so today we're going to talk about a new equation, and we're going to derive it. And it's something that you're going to learn in physics as well, if you haven't done so yet. It's called the root mean square velocity. Squared velocity. And it's actually kind of cool to see where it comes from, because it comes from places that you already know. And I'm just going to derive it quickly. You're never going to be held accountable for deriving it. Just know where it comes from. And you will always be provided that equation. I actually wrote it up here on the board next to the smart board. But let's just start where it comes from. So you learned that kinetic energy in physics of any molecule or anything is what? Kinetic energy is what? Half mv squared. All right, so one thing that's important for you to be successful with this is to know what the units are on a joule. Okay, I hear a lot of people always saying, oh, Newton meter, but let's take it down even further. What's a joule? I know you guys know this. Kilogram meter squared over second squared. So that's what a joule is. So at the end, we'll check our units and make sure that we're getting the right energy unit. Another thing that you learned yesterday was the average kinetic energy of molecules, gas molecules, and that was 3/2 RT. Okay, so the root mean squared velocity is going to be combining these two equations in a way where, as opposed to having the velocity of just a single thing, like an object or one atom or one molecule, we'll end up using the average kinetic energy to find the average velocity of all the molecules in a certain system. So all I'm going to do is set these two equal to each other. So I'm going to get 1/2. Now let me talk about this m real quick. That is usually in what unit? Kilograms. Well, kilograms is great when we're talking about one thing, but if we're talking about a mole of stuff, we want kilograms of an entire mole. What's the kilogram, or grams, even just grams of an entire mole? How do we find grams of an entire mole? Molar mass. So what we actually put here, instead of just mass, we're going to put molar mass, because we want the kinetic energy of an entire mole of a substance. Does that make sense? So this molar mass, though, you have to be very careful when you use this equation. You have to put it in kilograms per mole. So instead of oxygen being 32, you'd put in 0.032. Okay? Be very careful there. So 1/2 m, we're going to keep v as velocity, v squared, and we're going to set it equal to the average kinetic energy of a mole of gas, which is 3/2 RT. Now our goal is to isolate the velocity variable. So all we do is subtract. So what's the first thing we want to do? Not subtract, I meant isolate. We're going to multiply each side by what? 2. So then we end up with molar mass times velocity squared is equal to 3 RT. Okay? Now if I want to get velocity by itself, what do I divide by? Remember, this is one substance. Divide each side by molar mass, and I get velocity squared is equal to 3 RT over molar mass. But then if I want to totally get velocity by itself, square root both sides, right? And I get velocity is equal to the square root of 3RT, and there's your equation. Now they do something a little different in chemistry. They go ahead and just make the v a little mu. Root mean squared is usually what they use as the subscript. And then same stuff here. Okay? So this is the equation, and you'll always be given that equation. And you use that equation to find the velocity of some sort of, the average velocity of a gas. Okay? Let's go ahead and do a unit check and see if we get the correct units here. So let's start, forget the 3. What's R? R is a new R, and I have it right here for you. Anytime you're dealing with an energy, you have to use the energy R. Since this is based on kinetic energy, we got to have the joule-based R, which is joules per mole K. I'm not worried about the number right now. I'm just looking at units. And again, I'll provide you with that R. You'll get used to them. I'll say energy R and I'll say gas R. Gas R is the 0.0821. This is the energy R. Okay, and our temperature's in what unit? K. All right, and what's our molar mass in? Kilograms per mole. Okay. So let's take a look and see what happens with these units. I see I have a joule there. So I'm going to break that joule down even further. And I'm trying to think of a way to write this so people can look at it. Remember, what is this actually? A kilogram meter squared over second squared. So I'm going to kind of insert that in there and cancel out accordingly. So, and I have to take the square root of all of this, right? So what cancels? What can we just get rid of? Kelvin goes away. Moles go away. Kilograms go away. And what are we left with? Meter, no, joules I'm replacing with that. So meter squared over second squared, square root of that. What is left? Meter, is that not velocity? Okay. Yay, I got hand waving. Velocity. I wish third period would have gone this smoothly. So yeah, I'm going to make them watch the video because I'll post online. Watch the video! Demo messed up. It was not. It was so fast. I just wasn't focused. So anyway, that's where this equation comes from. So I want to jump to a couple slides ahead before I do Graham's law and just work one more slide. Work the very last problem, number 13, on this topic. And then I'll talk a little bit about the theory behind some of this. So letter A. Consider the three identical flasks filled with different gases. In which flask will the molecules have the greatest kinetic energy? And then in which flask will have the greatest root mean squared velocity? So, greatest kinetic energy. What was kinetic energy again? We're talking about a slew of gas molecules, so we're thinking about average kinetic energy. And in chemistry, what is that? No, 1/2 mv squared is of a molecule. 3/2 RT. We never, I'm just telling you right now, we never use 1/2 mv squared in this class. The only reason I did that was to show you the derivation of the root mean squared velocity. So we never ever touch that. 3/2 RT. And I kind of mentioned this yesterday. Kinetic energy doesn't matter what size. What is it only based on? Temperature. It's totally temperature dependent. So, with that being said, which flasks have the molecules have the greatest? Do the molecules have the greatest? They're all the same. Why? Same because all flasks are at the same temp. And that's kind of how I want you to pose an answer like this on the AP. Use an equation to prove it. Don't just say, oh, it's only temperature dependent, so they're all the same temp. Why? Go ahead and show this equation. Just point to that, and then that'll be great. And then say they're all the same temp, therefore same. Okay? All right, let's look at letter B. In which flask will the molecules have the greatest root mean squared velocity? Root mean squared velocity was equal to 3RT over the molar mass. You don't have to calculate every single flask's root mean squared velocity. It's a big waste of time. You can, but again, huge waste of time. All you have to do is look at mathematically where that molar mass is located. This brings up two new characters on the wall. Fat bastard. Find him up top. Y'all see him? And Mini-Me. Think about Fat Bastard and Mini-Me running around Austin Powers' lair or whatever. Okay? And think about Fat Bastard the time he wanted to get Mini-Me in his belly and he chased him. Could he catch Mini-Me? No. Mini-Me is a lot faster than Fat Bastard. Okay? Because he can get in between other molecules or other things easier. So your small gases are like mini-me, and your big gases are like fat bastards. So small gases diffuse faster, go at a higher rate of velocity faster. And that makes sense because if you look at the location of the molar mass, it's indirectly related to the velocity. Right? So the smaller the gas, the what? The faster the gas. Make sense? And that's what I call the fat bastard mini-me phenomenon. So with that being said, let's take a look at the examples. On the AP, I would go so far to write the molar mass down of all three of these. So we know this one is 28, what's 16 and 12? Oh, that's 28 too. And this one's about 2, right? So what's your answer? H2 is fastest. Again, point to your equation because it has the smallest molar mass. Okay, so what we can now utilize root mean squared velocity for is the creation of something called Graham's law. You did do Graham's law in pre-AP. There's not a special place in your notes for this. It's already kind of done for you, so if you just want to watch while I'm doing it, you can always print this derivation out from the notes once I get these up online. But what we're actually doing is comparing in Graham's law the rate of one gas to the rate of another gas. Okay, so I'm just going to quickly derive this. It's really, really simple. Rate, are you okay with me assuming rate and velocity are the same? Okay, so this is the same as velocity. All right, so this is gas 1 compared to gas 2. If I have gas 1, 3RT over molar mass 1 is rate 1, right? What's rate 2? 3RT over molar mass 2. Awesome. I'm going to simplify this. What happens to 3RTs? They cancel, leaving me 1 over that and 1 over that. How do I simplify that? Nope. Molar mass 2 over molar mass 1. And that's, I leave that the same, rate 1 is to rate 2. So that's Graham's law right there. Boom. So what I use Graham's law for is either to find molar mass of a gas or to find the ratio of rates of a gas, knowing what the gases are and putting their molar masses in there. That's it. It's really simple. So let's go ahead and apply this to the next problem. Calculate the average velocity. Well, let's do 12 first since it's in our head right now, the whole Graham's law thing. Oxygen diffuses at a rate which is 2.2123 times faster than that of a reddish-brown gas. So we don't know this gas. We're going to call it gas X. And we know about oxygen. Determine the molar mass of the unknown gas. How do I know I use Graham's law? Because it's asking me for a molar mass and it's giving me the information about another gas to compare to it. Okay? So I'm just going to jot down rate 1 over rate 2 is equal to, remember they're catty corners, so the molar mass of 2 over the molar mass of 1. They're going to be opposite because of that flip thing that we did in the derivation. So, how am I going to do this? It doesn't give me two rates, but it does tell me something. The ratio, if this is 2.23 times faster, is it okay to put oxygen on top of X and say that this is 2.23 over 1? Yeah? Do you get that? If that's 2.23 times faster, we can assume that's a rate of 1 and that's a rate of 2.23. Okay, so now I'm looking for the molar mass of X, gas X. Putting it here, I've made it rate 2. So this is what I'm looking for up here. I am looking for that molar mass. What's the molar mass of oxygen? Okay, why is it okay for me to put it in grams per mole and not to kilograms? Isn't this all based on root mean squared velocity? Shouldn't I put kilograms there? Go ahead, Hannah. Because it's a ratio, since they're going to cancel each other out anyway, whether I put the kilograms on top or bottom wouldn't matter. Okay. However, up here when I do root mean squared velocity, I better put it in kilograms because it's only in there once. Here it's in there twice and it cancels. All right. So before we predict the molar mass, let's fat bastard mini-me this and figure out, is it going to be faster or slower than oxygen, this weird gas? Why slower? No, that wasn't the question. I'm sorry. It's slower because it says oxygen's faster. Is it going to be bigger or smaller is what I meant to ask than oxygen. Bigger because it's slower. So we're going to predict larger. Well, go ahead and solve and tell me what the molar mass is. So 159 grams per mole. Okay, last problem. Let's backtrack. Calculate the average velocity. It's not 1/2 mv squared. Average velocity is root mean squared velocity. And that's equal to the square root of 3 RT over molar mass. So we're going to go ahead and plug and chug. Now I'm going to make it big because I'm going to put units in there. So 3, what's my R? We got to do the energy R. 8.31 joules per mole K. And then what's our temperature in this case? We have to do it in Kelvin, and that's 298 K. 25 degrees Celsius is room temperature, so you'll know 298 K by the heart by the time you're done with this class. We use it so much. All right, what is the molar mass? This is where we got to be careful, remembering that joules is actually kilogram meter squared over second squared. We have to put this in kilograms per mole. Please make a note of this, star it, punch yourself. I don't know what you have to do to remind yourself to do this, but don't forget. This is the time when people mess up on this coming up test, right here. And on the AP. So what does this turn out to be? 0.004 kilograms per mole. Okay, go ahead and solve. Turn that on. The answer, 1,360 meters per